You have previously been shown that flaps are fitted to the trailing edge of the wing, and you have now been shown that ailerons also occupy part of the wing trailing edge. The resulting reduction in flap area reduces the efficiency of the flaps. On large, modern, high-speed jet transport aircraft, this reduction in flap area is a significant disadvantage, so design changes have been made to make the ailerons also work as flaps. Hence the name flaperons. When the trailing edge flaps move down, the flaperons also go down. Now the whole wing area has its camber increased, thus maximising the effect of the flaps to increase CL max. But what about lateral control? Think of the flaperon position with the flaps down as a new neutral datum. When a roll input is made, the flaperons move up and down from this new neutral datum and still provide a change in lift on both halves of the wing for roll control. Spoilers are usually fitted to large, modern, high-speed jet transport aircraft to help the ailerons with roll control. Spoilers are movable panels on the top of the wing. They are hinged at their forward edge and activated hydraulically. When raised into the airflow, spoilers spoil or disturb the airflow, thus decreasing lift and increasing drag. Roll spoilers are activated by the control wheel and move up on the side with an upgoing aileron, proportional to aileron displacement. You can see that the roll spoilers on the side with the downgoing aileron remain flush. Even with the flaps up, the roll spoilers continue to assist the ailerons with roll control. Roll spoilers have several advantages over ailerons. Roll spoilers eliminate adverse aileron yaw. Roll spoilers do not twist the wing. Roll spoilers do not develop flutter. Roll spoilers do not take up space on the trailing edge, leaving it usable for flaps. Because spoilers work by reducing lift, their use will always result in a net loss of lift on the wing. This is not normally a significant disadvantage. When selected by the pilot, speed brakes increase drag. The use of speed brakes increases deceleration and/or gives an increase in the rate of descent without increasing the IAS. There are two common methods of mounting speed brakes: wing-mounted or rear fuselage mounted. Ideally, speed brakes should give an increase in drag without affecting lift or causing a change in pitching moment. Fuselage-mounted air brakes are best suited to do this, but are only occasionally used on civilian transport aircraft. Modern high-speed jet transport aircraft usually use the spoiler surfaces on the wing as speed brakes. There is a speed brake lever on the flight deck that, when selected to up by the pilot, extends the speed brake symmetrically, thus increasing the drag. There are no speed restrictions for the operation of speed brakes. However, the design of the hydraulic operating system does give a blowback facility. That is, for the same selection from the flight deck, increasing IAS restricts the speed brake angle of deflection into the airflow. This prevents excessive buffeting at higher IAS. While being used as speed brakes, the spoiler surfaces will continue to assist the ailerons with roll control. To illustrate this, we will pull partial speed brakes. Now, when a roll input is made, the spoiler surfaces will move up or down about the datum of the speed brake selection. In flight, the maximum angle to which the speed brakes can deploy is restricted to prevent excessive loss of lift and excessive buffeting. But as soon as the aircraft touches down, there is a need to remove as much lift from the wing as possible so that the wheel brakes will have maximum effectiveness. In addition, there is a need to increase drag as much as possible. After touchdown, the air-ground logic system senses the aircraft is on the ground and removes the restriction on speed brake angle. When full speed brakes are demanded from the flight deck with the aircraft on the ground, the speed brakes deploy to a much larger angle than in flight. This is called lift dump.